So, as we start talking about dynamics and the forces that cause it, the first thing we have to realize is the difference between mass and weight. We tend to use these words interchangeably, but they do not mean the same thing. And in physics, it's very important to make sure we understand the difference. Mass really is about how much stuff we have. If you think it from a chemistry point of view, it's the protons, the neutrons, and the electrons that make up whatever it is that we have. The weight, on the other hand, is how those particles are affected by the force of gravity and how they are pulled towards other objects like the Earth or the Moon. In our last couple of labs, we rolled carts down ramps and we dropped balls and beanbags. And students noticed that as the things moved towards the floor or the bottom of the ramp, that they got faster and faster. And this is correct. Students correctly identified this as gravity. Up until the time of Newton, that wasn't the thought. And a lot of times people weren't sure what caused this acceleration. But it is the force of gravity affecting the object. What we also know now is that the force of gravity changes. It does vary from place to place on Earth, and the force of gravity is different on different planets or on moons or so on. So, what we're going to start off with is looking at how the different gravities can affect and result in a different weight. When we recorded the acceleration on the beanbag or on a tennis ball or a basketball, we should have achieved the exact same result every time. And if we were to clean up our experiments a little bit and record some really good data, we would see that every student with every object would be calculating the same acceleration. The acceleration here is approximately 9.81 meters per second squared. And we will use that as the acceleration due to gravity on Earth. So I have a piece of brass here that we have out of the lab, and if you can see it, it says on it that it weighs 300 grams. Now I said it weighs. That's the incorrect language. It has a mass of 300 grams, and that is the sum of all the particles that make up this thing. But what we're going to do now is we're going to calculate its weight. Once again, we see 9.81 meters per second square is the acceleration on Earth due to gravity. So let's talk a little bit more about what that means. We're saying that if I was to drop a baseball, that its speed will increase each second by 9.81 meters per second. So once again, in other words, let's say it was falling at a rate of 10 meters per second. And then 1 second later, we measure how fast is it going. It is now going 19.81 meters per second. The speed has increased by 9.81 meters per second. So once again, we've got this object that has a mass of 300 grams. When we're doing weight calculations, we want to use the units of kilograms. So I'm going to convert my 300 grams into 0.3 kilograms. And then I simply multiply that by the acceleration that it's undergoing. In this example, if we were to drop it, it would accelerate due to gravity at 9.81 meters per second squared. And that would give me its weight of 2.94 kilogram meters per second squared. And these are known as fundamental units. But for simplicity, we're going to call that a Newton. So once again, 1 Newton is 1 kilogram moving 1 meter in a squared second. We have our first and probably one of our most important formulas used in the dynamics unit is that F equals ma. The force equals the mass times the acceleration. You will also see it written as F sub g, and g meaning gravity, is equal to the mass times gravity. So the acceleration here is gravity, and so it's just F is mg. But it's the exact same formula, just the acceleration is accepted as 9.81 meters per second squared. Lastly, please note that if we took that object and put it, say, on the moon, it would have a different weight. The mass would still be 300 grams, but it would have a different weight. And so we would say that that is F with a subscript g for gravity, and that has a subscript of moon for the moon. And that would be equal to the mass times the gravity of the moon. We tend not to write in the g of Earth. We don't really need to do that because we're going to assume that everything that we do is for the Earth, except for the few times when we do the exceptions, like the moon or Jupiter or Mars. So lastly, let's calculate the weight of that object on different celestial bodies. So once again, we had a mass of 0.3 kilograms. And to find out its weight on the moon, we would simply multiply that mass times 1.62 meters per second squared, and we would find out what the newtons of weight would be on the moon. We could repeat this with the different forces of gravity, Mars, Jupiter, Saturn, or other places.